Hello everyone, and thanks for joining Cyber Talks today again. And today's topic is going to be a continuation of our discussion about process emulators. And more specifically, we already solved a lot of issues of CPU emulator by converting CPU emulator into a process emulator. We also had some special edition topic about rootkit emulator and how to change CPU emulator to emulate drivers. But today we're going to address the biggest weakness of both CPU emulator and the process emulator, and specifically performance. As I mentioned before, performance degradation might be from 5x to 100x on both CPU and process emulators. And the biggest threat for CPU and process emulators is very simple. We all know this type of code, that's a loop. If it's a regular simple loop, that's not a big of a deal. It just goes through it, emulates instructions and memory manipulation and so on. However, it can be loop inside the loop. Also, inside that loop, you might have some memory access, or for example, it can have a lot of iteration inside the first loop, then it exits, and it has more iteration in the second loop. And so in general, these type of constructions, especially if the code inside the loop is pretty heavy, might take very long on inside the process and CPU emulators. And for example, another obfuscation can be here is API call inside that loop, and maybe there is another API call here. So if you run such a loop on a regular CPU, this loop is quite fast, right? It just goes, and maybe it's going to take a delay from a few milliseconds, maybe a few hundred milliseconds. Maybe if malware is really obsessed to be evasive, it can take 10, 20 seconds, depending on the situation. But imagine now, even if it takes 1 second on a real CPU, if it's 5 to 100x due to this different manipulation inside that code, and now you're talking about 5 to 100 seconds inside process emulator. And of course, the way process emulator has been integrated into products is to analyze malware fast, analyze every file written on a disk, or analyzing files which added into autorun. In general, it cannot delay system by 5 to 100 seconds on every P executable, so even on a slow P executable. So this was very powerful evasion techniques against process emulators inside antivirus engines, and of course antivirus vendors has to respond. And we're going to specifically talk about what I believe two main solutions to the slowness problem, which already existed probably in 2009, 2010, kind of at the end of this era between 2005 2010. Specifically, we're going to talk about binary translation and hardware optimization. Most likely, you have heard about binary translation, but that would be in a very different context than the cybersecurity and anti-malware. What usually you would have binary translation for is if you have an executable, let's say we have MZPE file, and it was compiled for Intel CPU. And the problem we're trying to solve is to convert that executable to execute on, let's say, ARM CPU. So it would perform the binary translation from one assembly instruction set to another assembly instruction set, so that, let's say, a program which would compile for Intel CPU laptop could actually execute on ARM or maybe some other processor. So the main use of binary translation might not be a security solutions. However, the security vendors realize very quickly that it's actually very, very powerful. Let's see why. The way binary translation happens in anti-malware products is slightly different, though. We don't try to translate Intel to ARM or any other CPU architecture. Instead, the anti-malware product uses binary translation for different purpose. So when binary translation happens, and specifically a dynamic binary translation happens, the analyzer starts to analyze code from the entry point, and it finds the first function, right? That's the entry point. Then it finds and searches for all the branching instructions like jump, or call, or conditional jump, and so on, right? And then at the red, this block ends, and we know that function which we're here, now we analyze it. So after the function boundary is found, that function actually converted into a set of logical blocks, right? So every time the analyzer encounters the branching instruction, it splits the function on multiple blocks. For example, here it might be a branching with a condition. Maybe, let's say here it goes outside, and that's a call to a separate function, and then return. And maybe there's another block of code here. And then we combine, and maybe there is a loop which comes back to the original logical block. So each block, and they usually call logical basic block LBB. So we can do LBB1, LBB2, LBB3. So each block itself doesn't contain any branching instruction, meaning all the instructions inside the block are just flat. They all execute from beginning to the end. And so what happens next, I'll remove this for now, just to clean the space, is that binary translation engine is going to take every block and convert it into intermediate representation, and so on, right? Different basic blocks. And what does it mean to convert intermediate representation? So in the Intel assembly instruction set, we have registers like EAX, EBX, ECX, and so on. They can simply be mapped as registry 0. Let's say EBX can be mapped to registry 1, and so on, right? So all registers can be mapped. The instructions, like branching instructions, can be mapped from a specific to CPU implementation to just be a branching instruction, and so on. So every instruction is normalized and mapped into this intermediate representation instruction. And usually after that, what happens is those logical blocks converted into a new CPU architecture. Right? So for example, if that would be just a regular binary translator, it would convert it from Intel to, let's say, ARM. But it's not a regular binary translator, right? That's a security anti-malware binary translator. So what it would do, it would actually convert all of these blocks into Intel again. And you would say, like, what's the purpose? We have an Intel program and we're converting it back to Intel. Isn't it just waste of resources? Wait a second. When it does that translation, first of all, it already split it and illuminated all the branching instructions, so it controls how to connect those blocks between each other. It also can analyze every single instruction, and let's say if it finds syscall or it finds some move of the value to a certain memory region or something like that, it can convert and sanitize every single instructions. Right? So what happens here, instead of really translating to a different CPU instruction set, it sanitizes the existing code to be safe to execute on a customer machine. Because now when this new code is built, right, these new blocks of code are built, when the translation happens, we can say, oh, instead of syscall, we're gonna actually call our own handler and embed this call right here in this new code. So this new code does not look like original code of a malware. It's sanitized, it's instrumented the way anti-malware product wants. And the cool thing about this is this code is not going to be emulated with a penalty of 5 to 100x. Instead, this code is going to be directly executed on the CPU. So instead of, if this runs, right, if we would just emulate this code, we would need to do emulation on vCPU. Then this code actually can run on real CPU. So the way it happens, after it's generated, it actually jumps to it loads all the registers, it jumps and executes this code, and as soon as the logical block ends, it has a choice. Either load back all the registers to vCPU and exit to the binary translation engine, or it can also link certain blocks between each other if, for example, it knows that they executed one after another all the time. For example, if this is the call to of API, it can link the emulation of API here and then link all 3 blocks together as a constantly execution block of code. But I don't want to go too deep into details. If you want to learn more about binary translation, there is an amazing project called QEMU, and specifically part of QEMU called TCG, which stands for Tiny Code Generator. engine, and it's open source, and that's actually responsible for translation to intermediate representation and the code generation. But what you need to remember is that the binary translation, the way it's used in anti-malware is it would analyze the code. It means it disassembles it, splits it into logical blocks, then converts it into intermediate representation, and then again generates Intel CPU instructions, but now all the instructions are sanitized and the code is actually instrumented in a way anti-malware fully controls the execution flow. It actually can log the execution and so on. So the heavy lifting, most of the performance penalty is incurred during the translation. And then as soon as the code is translated, it actually executes pretty much with the speed of a regular application. Maybe it has a little bit of overhead due to extra instrumentation and sanitization of the code, but let's say the performance penalty here would be 1.2x, while here it would be one-time cost during the translation. So this approach would be very powerful, but of course it's also going to take time to translate those instructions. And it means anti-malware engine might not apply this approach on every single binary. Instead, it still would apply it on a binary where it can spend maybe a few seconds for analysis. For example, it's a binary first seen ever on this machine or globally, and then anti-malware engine can spend a little bit more time analyzing it. But that's how binary translation is used in anti-malware engines. So let's talk about other method called hardware optimization and how that helped solve this issue, even making it even faster, but maybe a bit less controllable. The problem statement for hardware optimization is pretty much the same. We have a code which executes too slow inside the process emulator and CPU emulator, most likely due to heavy loop, meaning a lot of iteration inside the loop, or specifically a lot of noisy instructions. For example, at some point to evade process emulators, polymorphic malware would generate a lot of extra code. Also, it wouldn't be that simple loop. It would be what you might heard as a spaghetti code, where it would be a lot of different loops, and they all would be nested, which would be might take a lot of time to actually run inside the process emulator. So how do we do hardware optimization? Especially at the time between 2005 to 2010, we're not at the point where the CPU vendors started supported hypervisors out of the box. They're not widely available, so couldn't use them yet for optimization, hardware optimization, how we would do it now. So we don't really have this ring -1 and the hypercalls or any of that fancy things here at, let's say, with 2010. How do we do hardware optimization? So while the emulator would go through this code and emulate it, right? It would emulate how the execution goes, and maybe it says, okay. And it detects that this loop, right, specific that path of the loop, takes many iterations, right? It goes and emulates and emulates and emulates. Maybe it has a certain counter inside binary translator instrumentation, or maybe just emulates instruction by instruction. And it sees that, let's say, it has been already 500 iterations over that code. What it can do, and this one all happens in the process one, right? So it's a process virtual space of first process. It's under control of emulators. So there's an emulator instrumentation and so on here, right? Like vCPU and memory manager and so on. So what it can do, it creates the process 2 as an absolutely empty memory space, right? In Windows, you can create a process memory space which would not contain any DLLs or anything inside at all. And what it can do, it can say, okay, I only care about these blocks of code, right? And these loops. I would copy those blocks to that another process memory space. And I would only copy those instructions. The rest of the process memory space is empty. And let's say this code might be addressing some of the memory here, right? This memory instruction. So it actually needs to copy certain data, right? If this instruction accesses that data in the process 1, we copy this data into process 2 as well. And then what happens? We just allow it to run on CPU in context of process 2. So this code would execute inside that loop maybe another 1,000 times, maybe 10,000 times, maybe 100,000 times. But at some point, it will either take this or that branch, which simply doesn't exist in this process memory space. So it will throw an exception. When exception is going to be handled, the context, the current context of the CPU is going to be moved back to a virtual CPU here. And then emulator can just simply continue emulation. Of course, this data, if it was mapped between two processes, it may be even the same physical memory. We might copy the data from one process to another. It all depends on implementation, the specific product. But the idea is to remember, since we didn't have a hypervisor, we would copy the specific memory, specific code blocks from a process which we emulate to an empty process space, and we would just simply execute it until exception or some sort of access violation happens, and then the extra code would analyze this exception, this process, the access violation, or whatever happens here, and it would merge the execution back into emulation. Of course, very often that actually this instrumentation would require a kernel driver as well to catch all the exceptions and be able to access memory of the two separate processes and make it harder to evade such a system, and also harder to malware, for example, to escape this secondary process, and so on. So again, it all depends on the specific implementation of the vendor. We're not talking about those, but the idea is pretty simple. Copy the loop, execute it on the real CPU very fast until it crashes, merge the state back and continue emulation until next loop, identify the loop, copy to process 2, execute it, copy the state back, and so on. So that's actually pretty cool. What we're losing in comparison with the binary translation is when the code executes, we have zero visibility into that code. So that might be one problem. Another problem, if inside that loop we have an API call, we would need to add an extra code here, for example here, to emulate this API here, which might not be very easy. So depending on the complexity of this API, it might be doable, might not be doable. If it's a simply return 0, no problem. If it expects some more complicated logic from the API, it might be hard to embed it into the empty process space, especially if there are many different APIs. But the advantage is, of course, it's a CPU-like speed and no need of translation, right? As soon as you identify the loop, you copy it, you execute it, kind of zero delay, while in binary translation, you would need to identify the code, convert it into an intermediate representation, from intermediate representation generate sanitized instrumented code, which might take a lot of time. Especially for multi-layer polymorphic engines and polymorphic packers, this approach might be more efficient than a binary translation, while binary translation gives you a full visibility in every instruction. Okay, so we talked about binary translation and how it was used in anti-malware engines, and as well as hardware optimization. The thing to remember, binary translation is very high visibility into every instruction, can be very efficient and fast. However, the translation itself takes time, so it might not be always applicable. On the other hand, hardware optimization might be very handy when you're unpacking multi-layer polymorphic engine and need to run a lot of spaghetti code with no real visibility. You don't need the visibility there. You just want to run through it. So you don't have visibility, but you have very quick, pretty much hardware speed of execution of the polymorphic engine. And those two techniques, I think they were main techniques of how to fight polymorphic layers of malware, and we use in different scenarios by different anti-malware products. If you want to know more about virtual machines, binary translation, and you're really interested in this topic, I would recommend you to read this book. You might not need the whole thing. It goes into very deep details on the virtual machines, but definitely the first third of this book is must read if you're interested in the CPU emulation, process simulation, virtual machines, and want to have better theoretical knowledge of how that works, since well, Cyber Llama Talks is an amazing source of information. In 10, 20, 30 minutes, we cannot cover all the details. I also do recommend you a couple of open source projects like QEMU, Emulator, look at the TCG, tiny code generator engine, as well as I believe the Unicorn project, which is focused on specifically code emulation and easy instrumentation on top of it. So I will add the links below the video on the projects which I really like and believe very useful to learn. And yeah, of course, as always, subscribe, share the video, give me feedback. If you like it, give me feedback. If you don't like it, I do appreciate any feedback in general. So subscribe, and I see you next time. Thank you very much.